Hello, I'm Anum and I'm working on Stein's method for adsorption mixture graph models. So first, what are adsorption mixture graph models? So they are model for networks, and what kind of network? It's a special case of stochastic block models when our the nodes in the vertices are divided into a partition into groups according to some characteristic of interest. And the special case is in adsorption mixture graph models, we know the group identification of each node. So, for example, in this political block network from Atomic and Glance, the networks are the political blocks, and they are divided into two groups according to their political affiliation. So the red ones are the conservative leaning blocks, and the blue ones are the liberal leaning blocks. And the edges between the nodes are the number of citations between two blocks. So again, the color describes the type of the vertex. The red ones are the edges between the conservative blocks. Blue ones are edges between liberal blocks, and the orange ones are the edges between one liberal and one conservative block. So what do we want to do with this this type of network? So some research questions are, we want to understand the underlying community structure. So you might have heard about the community detection and that sort of thing. But here we are actually saying that we already know the group affiliation of the nodes, but we just want to understand how are these communities working underlying. And what else we want to do is we want to validate edges, or we might want to predict edges, or we might be interested in the underlying subgraph structure of the graph in ER mixture graph models. So to do this, since ERMG is a parametric model, so we want to estimate the parameters. We might want to assess. So we want to assess the goodness of fit, and we might be interested in approximating the ER mixture graph model with some simpler model or some model of interest. So we might want to want an approximation result. So we have looked how the ER mixture graph looks like. So this is how it mathematically looks like. It's simply the mixture of different ER models, an ER model within each group and an ER model between two groups. So here Nij is the number of possible vertices of each type. Tij is the number of edges in the observed network X, and Pij is the probability of an edge between a vertex of type I and a vertex of type J. So this is how the ER mixture graph model. Again, we are considering a simple graph with a simple undirected graph with no self loop, no multiple edges, and the vertices are all labeled. So what we did is we did the Stein's method for the ER mixture graph models. You've already heard something about Stein's method. So the Stein's method would give us a way to upper bound the distance between the ER mixture graph models and some other model of interest. So to give a Stein's method, we first need a Stein's identity. And then once we have a Stein identity for some test function, we can define our Stein equation. And then we can do other stuff that we want to do with Stein. So for ER mixture graph models, we have our, as you heard earlier, for the graph models, we can use the generator of global dynamics Markov chain as you'd say, as a Stein operator of the Stein operator. So in this Stein operator, the Q is the conditional probability of observing an edge at asset pair of vertices given the rest of the network. So in our case, it was simply the probability between, because the edges are independent, so it is simply the probability of an edge between at the vertex pair S. So we have the Stein identity, we have a Stein equation. Yeah, and we have this bound. We have a bound on this difference of solution of the Stein equation. So you have already heard that, which is if you have this difference, we can do a lot just with this one bound. So what we did is, once we have our Stein methods all set up, we can just bound the distance between the ER mixed graph models and some other candidate models. So what we did, we actually bounded the distance between the ER mixed graph models and ER models. So ER models are simply the Bernal random graphs when we have vertices, edges, and all the edges are they have same probability throughout the network. So all the edges have same probability, yeah, so the simplest model, network model. So we bounded the distance between ER and ER mixed graph models, and then we bounded the distance between ER mixed graph and exponential random graph models, and then we bounded the distance between two different ER mixed graph models. So why two different mixed graph models? So as I've told earlier that in ER mixed graph model, we actually partition the nodes according to some characteristic of interest. So this is possible to have more than one characteristics, to know more than one characteristic about the nodes. So let's say in political block networks, one was the political affiliation, other might be maybe age, education, or any other characteristic. And we might want to see that if we create an ER mixed graph model according to one characteristic, and then a different ER mixed graph model according to some other characteristic of interest. So how far apart they are, if they are far, or the distances. So what could be the distance between these two? So and then we might be interested, though even we are partitioning the vertices according to just single characteristics, but we might be interested if we have different edge probabilities under two graph models. So one example that I always give is, so let's assume that we have one set of parameters that are true, and the other might be that maybe estimated from some estimation method, and we see that how far under these two parameter sets, how far the graphs ER mixed graphs are. Another thing that we might want is we might want to refine the group structure of the ER mixed graph models. So when we talk about refinement, we say that so we already have these blocks, and we might know something else about these blocks, and we want to refine these blocks by dividing some or one or more groups into further subgroups. So then we want to see if that refinement actually makes some sense, that actually have that make a difference or not. Then we compare the two. We actually bound the distance between two ER mixed graph models. Again here, so the Pij is the same. The probability of an edge between the between type I and type J, and the AB is the so it depends also the indicators that in which subgroup we are talking about, which subgroup is in the node is in which subgroup. So we have all these bounds. So what are we going to do with this bound? So as an example, we actually evaluated these bounds for two real data networks. One that we have I just talked about, the political block network, and the other that you have heard in the morning, the Florentine marriage network. So for the political block networks, this bound is between the distance between ER, which is the simpler model, and the ER mixed graph models. So this is what we got. And for the political block network, so the Florentine marriage network that you saw earlier in the morning, it didn't have any partitioned vertices in it, but we do have you can say a covariate, which is the wealth data of the families. So what we did is we actually created two groups according to the wealth group. One group with wealth below median. So we just took median as a dividing point. So one group with wealth below median, and one group with wealth above median. So the size of the vertices in this graph just show the wealth of the families, and that is what we got after we divided the groups. So the red ones are one group, the blue ones are the other groups. Again, similarly, the red edges shows between the edges between red group, and the blue shows edges between red, and the orange one shows the edges between two different groups, versus from two different groups. So when we calculated our bound for this network after partitioning it, so this is what we got. this is the bound on ER and ER mixture graph models. And then this is the bound. This is another exercise. This is the bound between the ER mixture graph and exponential random graph models. So looking at this bounds. So this is the bound between the on the distance between two graphs. So looking at this bounds, is this distance small or large? So so looking at these bounds, we just say that maybe the ER approximation is not very horrible for the ER mixture graph models. So since the bound is not too big, so it gives them some intuition that we can use the ER model to just approximate the ER mixture graph model with the given parameters. So is it enough to say that the ER approximation is good enough for the ER mixture graph model just by looking at this bound? So we have no standard by saying that how large it should be. It just gives us some theoretical guarantees, but we can't give any concrete conclusions about the fit of the model. So for that, we need the goodness of fit test. So we give the goodness of fit test for the ER mixture graph models using graph kernel sign statistics that you've already heard in the morning. So which actually depend upon the kernels of the reproducing kernel Hilbert space. And we actually run some experiments to see if our test has some power. And we so we simulated the networks from the null model, and we then simulated the networks from different alternative models, and we just plotted the rejection rate for our test. And it seems that our test has power and a controlled type 1 error. So what we did is, we fixed the between group probabilities and just varied within groups. We fixed the within group edge probabilities and varied the between group edge probabilities. So this is and we got these results. So we also run simulation experiments for the parameters that we got from Florentine marriage network, and it seems that in that parameter regime, the test also has power. So just for revision, so this is what the test look like. It just again depend on the kernel of the reproducing kernel Hilbert space, and yeah. So this is what we have done until now. So we have the Steins method. We have bound on the distance between the ER mixture graph models and some other models, and we have a goodness of fit test. So in the next, what we are doing is we are if you have observed, we just plotted the curves for different null models. So we are looking to compare it with some underlying base model, so we can see if we have some advantage like Lude test. So if our test has some advantage over that model, so we are still working on it. And next we want to investigate the detectability threshold. So detectability threshold is as I said, we have these communities, and there are two types of edge probabilities: one within the groups and one between two groups. So when we do the community detection, so there is a bound that if the difference between the within and between is just below that bound, then the community detection algorithms can't actually detect the communities. So we are also working to see how we can use our test in that scenario. And then we will so there is a GKSS for edge resampling, and then we will just want to do the estimated GKSS for the political log and Florentine networks, and maybe for any other network. So this is what I have to tell you today, and thank you. And I will welcome any question that you have.
Thanks, Anna. Any questions? I have a question.
Yeah.
Forgive my ignorance on this topic. Where are these types of graph models applied?
where are these graph models? So
where are they? Like, yeah.
so we have a graph data like this vertical block data, and there are so as Gina mentioned, there are networks which are so fraud, which are detecting, so bank transaction networks. There are biological networks, protein networks. So the network data actually appear in a very wide. So there are networks which are the you can say the in city transport networks. So networks appear in various fields, and they are complex data, and we the already present methods only deal with some, just to look at some statistics from the networks and just base conclusions just based on them. So these are derived that we need more concrete or if we have the underlying models, we can do better approximations, we can do better inferences, we can do better what we want to do with our networks.
Yeah. ERMGs are generally applicable for all graphs, but more.
So ERMG are when you know that your graph has some community structure. Yeah. So there are graphs when we know the community structure, and there are graphs when we don't know the community structure. That's also a future work where we don't already know the community structure, and we also want to predict the community structure and the probabilities and the things of that.
Cool. Thanks. Any more questions? Well, I have a follow-up to my question in that case.
Yeah.
Are there separate tests for presence of community structure?
There are different methods to just detect community detection. So, Vizina, would you? So I'm not very familiar with because I'm not there yet about the community detection. Maybe Vizina can just tell us a bit better.
If any mixed models, people could look at live duration.
Yeah. Yeah, and there are different methods. Yeah, there are different machine learning methods available to just detect communities, and they give you communities, but they are not all too good. Sometimes they just. Right. So I try to for the Florentine marriage network, I actually manually created these communities, but I run few of these community detection algorithms, and they just give me completely off communities. So might if the Steins method might maybe somehow lead us out to some better community detection. When we in this project we are not we already know the communities, but we will be working when we don't already know the communities, and yeah, we also estimate the communities and then do the Steins method.
Yeah, people also look at modularity for community detection, and then they run Monte Carlo tests, so they just simulate the model, see whether the modularity is maximized.
Yeah.
By the specificity. The problem is that something like the like real world networks, like the political block networks, they don't maximize their own modularity.
Yeah.
Yeah.
And sometimes it gives you a community that actually that are difficult to actually describe. That like here we have political affiliation, so something the community that don't make any sense. So yeah, so that's something challenging.
Unless there's any more questions. Cool. Thanks again.
Thank you.